Okay, so in the last video we were looking at logs and introducing kind of logs generally and converting from log to exponential form and solving some kind of simple log problems and rewriting and simplifying different terms using our log rules. And one of the last things that I touched on was just common logs that are used. So one that we have here is log to the base 10. And log to the base 10, as I said in the last video, is often just written as simply log with no base number. So we might see something written as log of 100. And the answer to that, if you check, and you can check it on your calculator, would just be 2. And that is because as a common logarithm, it's just understood that if you write log down with no base number, that means it's base 10. Similarly, we have log to the base e. We've said e is an irrational number, okay, similar to pi. E is kind of a particular number that has a particular value. And if we have log to the base e, that's also called ln, or the natural log. So we see that on our calculator as well. So if we saw ln of 2, that would be the same as log to the base e of 2. And you can try that out on your calculator by using that ln button, but also using your log button that allows you to input the base. E is a value on your calculator. So you can see that they're the same thing, that we can move between them fairly easily. And we might see these types of logs in particular questions. ln particularly, that natural log, comes up a lot to do with certain kind of real life scenarios. So when we're looking at radioactive decay and the growth of cells and things like that, we might see that natural log quite a lot because they all tend to work with our exponential growth and with our exponential formulas, and a lot of the time it will be with that e value, okay, with our natural exponential value. But just a quick kind of recap on those common logs, because we're going to be using some of them in this next section, which is on log equations. So I've written down some key points here, and let me just move it down a little bit so that it's on the lines. There we go. So some key points for us when we're looking at our log equations. So the first one is when we're solving log equations, we have to check that the bases are the same. So we saw this in the last section, that with most of these rules, we can't use the rules unless the bases are the same. And if it's a case that the bases aren't the same and we're not going to be able to do anything, we may need to change the base. But we're able to do that. That was one of our rules that we saw. The next point there is if we have log to the base a of b is equal to log to the base a of c, then that means that b is equal to c. And I've written in there that symbol in the middle, kind of a vice versa symbol. So what it means as well is if we have b is equal to c, then that means log to the base a of b is equal to log to the base a of c. Okay, so what it means here is generally b is equal to c. Okay, that means that they're the same. That equality obviously means the same. So if two things are the same, then the power to get to both of those things will also be the same. And this can come in very handy with log equations, this idea that if we have two things on either side of an equals sign, that we can rewrite them in log form and they will still remain equal, because that's not always true with all of our operations in maths, but it will work for our logs here. The last point then is that we need to check our solutions. So not all our solutions are valid. We cannot have the log of a negative number. And we might think about what that means for a second. So what we mean by that is, for example, we cannot have log to the base 2 of minus 4. And if we convert that to our exponential form, what we're saying is that 2 to the power of something is minus 4. And there's no way that we can have that. Okay, we can't have 2 to the power of something being equal to minus 4. There's no way that we can do any sort of power of 2 multiplied by itself that would still give us an answer of minus 4. So we saw in the last section that the answer itself, the value of the log, could be a minus, because we've seen that with our kind of fraction conversions, but we can't have that the subject part is a negative number. So let's look, moving between exponential and log form. Okay, so if we're looking to move between exponential and log form, we need to try one of these two methods, and the first method is going to be the one that we've been using all along. Okay, so we simply take our base number, we write it down here, we take that subject term down the bottom, and we write it being equal to x. So instead of writing 3 to the power of x is equal to 27, we're saying log to the base 3 of 27 is equal to x. And then at that point, we could use our calculator. And we could type this into our calculator, or we could simply kind of know the answer for ourselves, but we could type it into our calculator and we get that x is equal to 3. Okay, because 3 to the power of what is 27? It's obviously 3 to the power of 3. So that can be perfect for most of our questions. Sometimes we'll have more complicated questions, and doing it in that form can actually just end up confusing things more. So sometimes what we want to do is we will take the log of both sides. Okay, so that's what we're going to consider it to be. We take the log of both sides. And this actually comes from this point up here that we were talking about earlier. This idea that if we have two things that are equal, then if we take log of both sides, if we rewrite them with this log operator, they're still going to remain equal. Okay, so that's what we're going to take a look at now with this question. So if I rewrite this one, 3 to the power of x equals 27, I'm going to use a log operator. It doesn't matter which of the logs I use. I could use log to the base 3 here because that might be handy for what we're looking at. But in actuality, I can use any. So I'm just going to use that common log of just log to the base 10, or just log. Because in many ways, we're just writing this down in order to have something, to have a log form introduced. So a lot of the time, because we're using a calculator as well, it doesn't necessarily matter what log we're using. And sometimes it will be more useful to use one base than another, and we saw that with our ln, but a lot of the time it's a case of just introducing log of both sides, just so that we can work with it. So now using our rules, we should know that if we have a question like this, where that subject in the middle, that bit in the brackets, has a power as well, that power can come down to the front, and we get log of 3 is equal to log of 27. Now, even though we're introducing these logs and we're working with logs, they still follow the same ideas as we've always had. So we can think of it as another variable. It's still a number, so we can still divide by it. And we get that x is equal to, if we use our calculator, so we can use that log form that we've seen here, and log of 3, and we get our answer being 3, which is what we expected. That's what we had on the left-hand side. So that version on the right-hand side for this question seems a lot more complicated. And in many ways, I suppose it probably is. It's probably a bit overkill, but for some of the questions that we're gonna see, we might need to use this idea of taking log of both sides. So it's important to be familiar. In actuality, you'll probably end up using the right-hand method, that method 2, more than you'll use the left-hand method, because the right-hand method tends to be a bit easier to work with because we've logs on both sides. And particularly when we're using our calculator, we can work out these things a lot quicker. So the log of any number becomes much easier to find. So looking at this example, 2 log to the base 3 of x is minus log to the base 3 of 18 minus x is equal to 1. Okay, so we need to work out how we're going to deal with this question. And the best thing we can do is try and tidy up the left-hand side first. So instead of writing this first term as 2 log to the base 3 of x, we saw this in the last section, we can rewrite it as log to the base 3 of x squared. We're going to leave everything else for the first run through here, and it's still log to the base 3 there, sorry, is equal to 1. Okay, let's continue on. So we're going to have log to the base 3 of, using our other rule, we know that if there's a subtraction, we can rewrite it as those subject parts divided. Okay, so we can see here that this and this part have merged here, have become a division here. Now we know 3 to the power of 1 is equal to x squared over 18 minus x. So that's what we can rewrite here. 3 to the power of 1 is x squared over 18 minus x. And what have we done to go from one step to here? We've converted from log form to exponential. So from log form to exponential form, and that's completely fine. We're using that first method backwards. Okay, but what it allows us to do now is, so we've rewritten our question, 3 is equal to x squared over 18 minus x. We can multiply by that bottom part, so 18 multiplied by 3 is 54. 54 minus 3x is equal to x squared. We can tidy up our question a little bit more, maybe bring everything to the left hand side. X squared plus 3x minus 54 is equal to 0. We're looking for two numbers that multiply to give me 54 but add to give me 3. Okay, so that should be 9 and 6. So we're going to get, let's see, x plus 9 and x minus 6 equal to 0, and then that means that x is equal to 9 and x is equal to 6 and x is equal to minus 9, So minus 9 plus 6. Okay, the last thing that we said when we were looking at these rules was that we have to double check, we have to verify. We've seen this with a few different operations. Our surd operation was something similar, and we saw something similar with our modulus as well. Just making sure that everything works out, that everything's verified. The surd was the big one that we had to verify at the end. So let's have a look. 2 log to the base 3 of minus 9. Okay. Are we immediately seeing an issue? Can I have log to the base 3 of minus 9? Is there any way that 3 can be to the power of something and give me minus 9? But if we're unsure, we can try it out in our calculator. 3 to the power of log to the base 3 of minus 9, and we get a math error. Okay, so what that means is x minus 9 is not valid, is not a valid solution. Okay, we can't have that solution. If we try the other solution over to the side here, so 2 log to the base 3 of 6 minus log to the base 3 of 18 minus 6 is 12. Okay, working that out, again, we can use our calculator here. We don't have to work these out for ourselves. Log to the base 3 of 6 multiplied by 2. 3. So, and we can really type the whole thing into our calculator here and just see what answer we get. And we get an answer of 1. And that's what we expected. Okay, that's what it should be. So we're verifying our solution, so it should match the right hand side. So what that means for us is that x equals 6 is valid. Okay, it's valid. Okay, so let's look at another example. So here we have log to the base 3 of x plus 3 log to the base x of 3 is equal to 4. So immediately we can see that we have an issue with bases here in terms of what we're looking for. What I would personally do is change this one here so that we can remove the x from the base part. So I'm going to first of all look at rewriting this question. So we can rewrite it as log to the base x of 3 to the power of 3, which is equal to 4. It's just changing that 3 in the front, just bringing it back into my question. So now we have log to the base x of 27 is equal to 4. Then just trying to change the base of that second term becomes log to the base 3 of now 27 over log to the base 3 of x. Okay, and matching things up, that 27 was what was here, so that's perfect. The base 3 is what we wanted, and the base x was what we originally had. Okay, and equal to 4. Now, just tidying this up a little bit, we could even work out this top part. Log to the base 3 of 27 we already know is 3, and that's log to the base 3 of x is equal to 4. And what this might remind us of is some of the exponential questions we already did. So what we're going to do is we're going to let y equal to log to the base 3 of x. We're going to get y plus 3 over y is equal to 4. Okay, so we should be seeing this familiar. This is our quadratic questions that we had already. We can multiply across by that y there. We get 4y, tidying things up a little bit. Minus 4y plus 3 is equal to 0. And of course we get that y is minus 3, y is minus 1. So y is equal to 3, y is equal to 1. The last thing we have to do is verify. So let's bring this over to the side, or sorry, not verify. First of all, we need to go, well, now we know that y is equal to 3, but of course y is log to the base 3 of x. So log to the base 3 of x is equal to 3, which means 3 to the power of 3 is equal to x. So x is 27. And of course, again, we have log to the base 3 of x is equal to 1. 3 to the power of 1 is equal to x. So x is equal to 3. Now to verify our answers, we can look back at our original question and we can sub in. So log to the base 3 of 3 plus 3 log to the base 3 of 3 Log to the base 3 of 3 is 1, plus 3 is equal to 4. So that's correct. We can try it then with our 27. So log to the base 3 of 27 plus 3 log to the base 27 of 3. So log to the base 3 of 27, we've kind of already looked at. Log to the base 3 of 27 is 3. Log to the base 27 of 3 works out at being a third. And 3 plus 1/3, okay, but it's 1/3 multiplied by 3, so that works out to give us 1, and that gives us 4. Okay, so we can see that both of those are valid. So we can write down that they're both valid solutions. So they're both valid solutions. So we can see there is similarity between some of the questions that we've seen in our exponential section and now this log section. So we had to substitute in for that log to the base 3 of x. So an interesting question, just kind of pushing us a little bit further there. Lastly, I want to look at a question where we have to do this taking the log of both sides, just to see what it looks like. So here we have y is equal to 2 to the power of x minus 1 plus 3, and we're asked to express x in terms of y. We can see that x is a power up here, okay? And in terms of our logs, generally if we want to work with powers, we need to introduce logs somehow. And the best thing that we can do is get to a situation where we have log of something to the power of something, because then we end up being able to multiply that term at the front. So that's what we're going to try and do here, but in order to do that, we need to have that 2 to the power of x minus 1 on its own. So the first step we're going to do is we're going to bring that 2 over to the other side. We're going to subtract that 3, or the 3, sorry, we're going to subtract the 3 from both sides. So we end up with y minus 3 is equal to 2 to the power of x minus 1. What I'm going to do at this point now is I'm going to introduce this log operator. I'm going to take a log of both sides. And this is coming from the idea that we had said earlier, that if we have two things that are equal, then taking log of both sides of both of those things should also be equal. But what it does mean is that we can rewrite this right hand side as now x minus 1 at the front here multiplied by log of 2. Okay, so we don't actually have to work those things out, we can leave it like this for now. Keeping my left hand side here, will not maybe move it yet. On the right hand side I can multiply my bracket out, so I get x log of 2 minus log of 2. Okay, so I can now look at the next little part, or in fact simpler than multiplying that out actually. Let me see, we'll go back, we'll make it a little bit easier for ourselves. Let's divide across by that log of 2 to save ourselves the hassle of having to multiply this out and then to rearrange it. So we end up with x minus 1, and then we can bring the 1 over to the other side. So we end up 1 plus log to the base, or log to the base 10 I suppose it is, or just log of y minus 3 and log of 2. Okay, so what we've done here at this middle step, so at this very first step, we took the log of both sides. Okay, so we took that idea that if A is equal to B, or if B is equal to C, I think it said, then log of B is equal to log of C. Okay, so we're allowed to do that. We can take log of both sides so long as the equals is there. The reason we had to move the 3 first was so that we could end up with this situation here, with the log written like this of 2 to the power of x minus 1 without that 3, because once we have it written in that form, we can rewrite it as we have done in the next line. Then we're remembering again that a log is a power, it's a number. We can divide across by them. And then just rewriting, we've written x is equal to 1 plus log y minus 3 over log of 2. And what they've said here now is hence find, correct to 4 decimal places, the value of x for which y is equal to 8. So y is equal to 8. So let's have a look. X is equal to 1 plus log 8 minus 3 over log of 2. 1 plus log of 5 over log of 2. And we can work that out in our calculator. So log, and we're just using that log operator. I'm adding 1 to the whole thing, and we get to 4 decimal places 3.3219. Okay, so the value of x for which y is equal to 8 is 3.3219. So we can see with a lot of these questions we will end up having to use our calculator. So we do have to get used to those log buttons on our calculator. We should also get used to those common logarithms and this idea of taking log of both sides that we've seen here. So if two things are equal, we can take log of both of those things, and that will generally allow us then to bring the powers down into a form that we can work with. So we see here how it allowed us to rewrite this equation. Instead of being in terms of y, we were able to rewrite it in terms of x. Okay, in the previous questions, we actually didn't really have to use that manipulation, that taking log of both sides, but we were able to see how, in this example, how changing the base was going to help us with solving that question and subbing in. And the same thing here then, manipulating the formula, manipulating the equation. But for all of these questions, the key thing was with an equation, obviously, we're solving for values of x. So making sure that when we solve for those values of x, that they're all valid. And then with this last example, it was that idea of just taking log of both sides. And that's something that we're just going to work on a little bit more, that we're going to look at some examples of. And we'll see it in further sections when we look at those real life problems.